Hello everyone. So today we'll be discussing mainly about the week 6 of doubt and problem solving session. So good evening everyone. Welcome to the week 6 of doubt and problem solving session in the course of carbon materials and manufacturing. I'm Saurabh Soni, and today we'll be going to discuss about the some problems and some good concepts which we have learned in this week, and we will so this week pattern will put like we'll have some numerical questions as well as some conceptual questions, and then apart from those few questions I'll be mainly discussing about the topics and the concepts thoroughly in this week. So yeah, so let's start. So let me just connect my writing pad. Yeah. So let's begin with our first question. Yeah. So our first question will be mainly the numerical type. So in this question, the question is asking calculate the UV dose. Okay, so here we have to calculate the duration of UV exposure in seconds. Okay, and for a resist film of thickness 5 micrometer, given the energy required for photoinitiation and cross-linking is 140 millijoule per centimeter square, and the intensity of the UV lamps is 7.5 milliwatt per centimeter square. So this is the question. If somebody has tried or know this question, then you solve. I'll be wait for some times, and then I will help you to solve this kind of a problem. So yeah, please solve by yourself. I will hold for some times and let me know. So the question is asking the duration of UV exposure in seconds. This you need to find out. So try by yourself. Then we'll discuss how to solve this kind of a problem. Yeah. So, hope you have tried. So, let us discuss about this. So, firstly, we will write the given that. What is given that? So, the film thickness is given 5 micrometer. Energy required for photoinitiation and cross-linking. Okay. So, the energy required is given how much? 140 millijoule per centimeter square. Then the intensity of UV, this is U. UV lamps are given how much? 7.5 milliwatt per centimeter square. So this is given, okay, and we have to find out the duration of UV exposure in seconds. So time we have to find out, okay. So there is a way. So I will give you a hint for this, and then I will give you the solution also. Okay. So here just now, like you have seen. So firstly, how we will do this? The method of doing this is like this. Okay. So firstly, we have to know that what is the formula. So this is UV dose equals to energy required for photoinitiation and cross linking. Okay, so here like we have seen energy required for photo initiation, okay, divided by intensity of UV lamps, intensity of UV lamps. Okay, but the interesting part here is always you have to check the units which are given. So if units are not mismatched, then you have to convert your units in the standard SI format. Okay, so here the energy required for this photon initiation is given in what? Millijoule per centimeter square. So you have to convert this millijoule to joule per centimeter square. So now here your 140 millijoule per centimeter square is equal to, if you will divide it by the 1000 to convert into zero, then it would be 0.14 joule per centimeter square. So this is your conversion, this is zero. Okay, now next you have to convert the intensity. So the intensity is given here in milliwatt per centimeter square to watt per centimeter square. Got it? So how much it has given here in the question? 7.5 milliwatt per centimeter square. So it would be 0.0 0.0075, sorry, this is 5 watt per centimeter square. Okay, now put in the formula. So UV dose equals to here, this would be your 0.14 joule per centimeter square divided by 0.0075 watt per centimeter square. So this would cancel out and this would come in second. So it will come around 18.67 second. Okay, this is your 18.67 second. So this is your answer. So what would be your answer? 18.67 second would be your exposure time. Hope you have got this. So how to solve this problem? This is pretty simple formula and a very simple way to solve the problem. Okay, so here you do not have to do anything. It is just, I will again explain this if you have not got this. UV dose, it means the energy required for your photo initiation, which has given in the question how much it has given for the photo initiation, and the cross linking is 140 millijoule per centimeter square. Okay, divided by your intensity of your UV lamps, and which has given 7.5 milliwatt per centimeter square. So convert into the SI formula, millijoule to the joule and milliwatt to the watt, and it would come around 0.14 and 0.0075. So divide these two and you will get the exposure time, which is somewhere around 18.67 second. You will get for the film thickness of 5 micrometer. So this is the way. Hope you have guys understood. If you have any doubt or problem, then you can ask immediately, and later we can move to our next question. Yeah. So let's moving to the next question. So the next question is very interesting and it is asking the question about the lithography. So here the lithography of negative resist involves an additional post-exposure baking step because what? It is required for cloth linking the resist. Negative resist do not degrade. Negative resist have a lower sensitivity. Negative resist films are thicker. Okay, so we have to thoroughly see about firstly, in order to understand this question, we need to know that what is photography, how it works, and here it is asking about the negative resist. Then how can we use, in what cases we use negative, and in what cases we use a positive one, that we have to discuss in a very detail. So let's begin. Okay, yeah. So do you anybody knows like what is photolithography, or has anybody done in previously? Do let me know. You can type in comment box, or you can comment in the chat box. Yeah. So what is photolithography? Photolithography, the in a very generic word, what I would say is the transfer of your pattern. Okay, so I will write here that photolithography. So what it is nothing but your transfer of your pattern. So this is called, in a very general term, we call it a photolithography. Okay, by the name itself it is clear, the photo. Okay, so there will be some kind of a design that needs to be transferred in some sort of a substrate, whether it could be any flexible sheet, it could be a silicon wafer, or whatever you take. Okay, so in a photolithography basically involves a patterning a structure using UV light onto a thin photoresistive polymer film. Okay, photosensitive polymer film. So there will be your structure of certain design that needs to be exposed in the UV light in order to transfer your pattern. Okay. Now the polymer is known as the photoresist, and which can be a two types. The first one is your positive resist. The second one is your negative resist. So in the case of positive resist, it gets degraded on UV exposure. Okay, so if you will be using the polymer which has a property of your positive resist, then it will degrade when you will expose to your UV exposure. But in the case of negative resist, it will be opposite. Here, it will get cross-linked after UV exposure, and it won't get degraded. Okay, and you require some post-exposure baking also in case of negative resist. So here, when you will do some UV exposure, it will get cross-linked, but here in the case of positive, that will get degraded. So these are the main two basic differences between the positive resist and the negative resist. Okay, now this involves 5 steps. So what are those 5 steps? We will learn thoroughly. The first one is your spin coating the resist film onto a substrate. So let's say we have a substrate of silicon. So first question is, as a researcher, you have to do some, you have to make some film or some mask, some pattern in your silicon. So what is silicon wafer? Okay, so basically silicon wafer is some kind of a, single crystal which looks like a circular. In some cases you can find in a rectangular way. Those usually used in the solar cell and all. But here usually what we use is in a circular format, and it could be different sizes, whether it could be a 4 inch or 6 inch like that. So spin coating. So you should know that what is spin coating. So spin coating is a process of making a thin film. Okay, let me take one more slide here. New slide maybe it would be a better to explain here. So spin coating, there will be a this circular kind of a pattern, and here you will have some vacuum chuck. Okay, and on top of this vacuum chuck your sample will place here. Okay, and this will rotate at very high RPM. So this RPM depends on, okay, so how you will set this RPM? The firstly it will depends on the viscosity of solution, whatever solution you have. So of the viscosity of that solution or any solvent. So on the basis of that you can set your RPM. The second thing is your film thickness. How much thickness you want? If you want lower thickness or very thin, then increase the RPM. If you want some thicker or the higher thickness, reduce the RPM. Okay. So nothing in film coater here. You just place your samples and drop down some your solution or whatever you want to make a film. And then after creating a vacuum and after pouring your solution, you give the RPM and it will start rotating in a very fast manner such that you will get a very uniform film of very thin. This thickness will be very less in the range of few nanometers. So this is nothing but your spin coating. So this is how you're gonna do your spin coating. Soft bake. Okay. Now the second thing is your soft baking. So in the soft bake, you can place in any hot plate kind of a thing here. Suppose this is your hot plate. Okay. So here you will place your sample which you have spin coated just now. So what is the reason? Why do we need to do this soft baking? So here in your solution, you will have some solvent. You will have some, it could be some binder also. Okay. So in order to remove this, you have to expose your material at certain fixed temperature. Got it? So let's say here if we will give a 90-degree. Okay. Here two things are important. What are the temperature you are giving and for how much time you are exposing or baking your film. So in order to get a proper baking so that your film can adhere or the better adhesion onto your silicon substrate, you have to expose your film for some particular temperature, for some particular time at some particular temperature that you need to optimize for your material. Got it? So here, this is a very important step each and every in your lithography. So these are some points that I am telling you in a very detail that could be very important for you if you will be using this. Then the UV exposure through a mask. Okay. So let's say here, this is your mask and this is your UV. This is your UV and this is your mask. Now UV is coming like this. So here in positive, what you have learned, it will degrade when it will get exposure to the UV light. Now, the only here, if you will see, the UV is coming from this side. This is your mask. Okay, this is, so this purple color will get degrade when exposed to the UV. And only from where the UV cannot pass, that will be remain unchanged. So it will be remain there. So what you will get in a final pattern, okay, you will get only this. This will be your end result. Got it? So here in negative resist photo initiation. So here in case this will be opposite. Now here this is the mask, the pattern, and this is opposite. Here UV is coming and this will get not degraded. This will get cross linked. So here it will be unchanged. Okay, this will be your this will be your cross link and this part will be your unchanged. Okay, so in the final pattern you will get this one, this and this will be your end. So this is just opposite to the what we have seen in case of your positive resist. Hope it is clear. Then not you can also ask me in the comment box. Okay, so after exposing to the UV, developing. Okay, so here you have to remove. So here the third one is your UV exposure. The fourth one is your developing. So in this case, what you will do, it will be like etching. Here you will put in some solution where you are in the case of your positive, the which uh, uh, the one which has exposed to the UV, that will degrade, and the one which has not exposed to the UV, that will remain. Okay, so this will be giving your final pattern. And at last, you will do the inspection under the microscope. You can use some any imaging technology such as your scanning electron microscopy. For further detail, if you want more, you can use some TM, or just you can use a high resolution optical microscopy. So the negative resist crosslink, hence the structure on the mask should be opposite of the desired structure. For the positive resistor, structure on the mask is same as what we want. So here it is again shown in a way that I have explained. So the first one is your spin coating. So here this is like your spin coater. Here this is your vacuum chuck where your this is your wafer. This is your okay, let me write here. This black one could be your silicon wafer. This is your vacuum holder, and this is your solution which you want to make a film. After making film, it will you give some heat, and it will bake, and then you will put your mask and expose to the UV light, and this will become this kind of pattern. Then you will put in some solvent or some solution, where in case of positive, the one which has exposed to the UV light, that will get degraded, and the your remaining will come as your pattern. And at last, you can do some inspection by using your imaging technology like SCM, TEM, or optical. And this is the way, so this is the kind of a pattern you can get if you will zoom in. So yeah, this is the main way of doing your photolithography. If you want to see in a more detail, and if you do not have any lab resources, then I would suggest you in the YouTube, you can get a lot of videos to gain a more knowledge about your photolithography, how it works, and in what application we can use this. So yeah, there is a lot of videos you can watch, and if you will have further any doubt, you can ask me in our next lecture. Okay, so I hope it is clear. If not, then let me know, and I can give a more detail about it. So yeah, I hope it is clear. No comments, no question. Then we'll go ahead and we'll see furthermore. The next is also it is also about the photolithography. So here, first thing is, as we have seen in our negative resist, we have some cross linking. So in our solution, so negative resist have a chemical structure, okay, that contains some additives which provide a proton after being exposed to the UV light. So during post-exposure back, the photon initiates a chemical chain reaction which creates radicals in its side chains. These radicals bond with each other and the polymer chains are bonded sideways. So this is known as cross-linking. Okay, so here you can see this is like uncrossed polymer, and here it will make some bonded, sideways bonded, and this is like a cross-link polymer. So resist viscosity and film thickness, like which I have mentioned in mentioned just in a previous slide, that you have to optimize your viscosity and film thickness in order to get a uh, uh, better film. So negative photoresist come in different viscosities, but same chemical structure will be there. One can make up to 150 thick films with them, which means that can be the height of the pattern structure. Okay, positive resists are used for making thin films. Negative for masking device. So negative can be used for making device such as MEMS, where you would require some layered kind of a structure. Okay, so here this is a very good key point, that the positive resist you can use if you want a very good thin film, but if you want some MEMS and for the device, then you can go for your negative resist, and that would be better. And the reason is very obvious, that I have explained just few minutes ago. So yeah, here you can see in this diagram, yeah, here you can see this is your silicon wafer, as you can see, like this circular kind of a shape, and here you have put some, this is gel kind of a your photo resist, okay, on top of your silicon wafer. Okay, so critical dimension, smallest feature size one can pattern reproducibly. Okay, you can give any critical a very small resolution, also you can get a very small creature size or the feature size one can pattern and with reproducibility. Clean room is a place where you do all this kind of stuff, patterning and all. So clean room is very the room where there will be no dust, no particle, because if you want to make any kind of a device, then you have to make sure the cleanliness of your atmosphere that you are using. It should not have any dust particle, should not have any contamination, and it should not have any kind of a toxic gases, so that's why it has to be clean in a very high level. So clean room is a one facility or experimental facility to conduct micro and nano fabrication. Okay, because if you will go to such a low level of work or the fabrication of your devices in a nano scale, then it would be very obvious and very important to maintain the cleanliness in your fabrication. So it has a multiple filters and a positive pressures. Okay, so you will in this room, if you will go, it's not like you will go open the door and you will get into the room. It will have a multiple filters, and it's like in the positive pressure, so you will feel a different pressure. So to ensure that there are extremely few particles that are greater than or equals to zero point 0.5 micrometer. So just see that how much cleanliness they are maintaining when they are fabricating a nano fabrication. So that's why in a country it is very important, and also that's why it makes the cost of this kind of a fabrication very expensive because it is very difficult, as well as it's very to maintaining such kind of atmosphere is very highly I mean very costly. So that's why enhance the cost of your devices. So clean rooms are divided into classes based on the number of particles per cube feet. These are like class 1. So in clean room also there will be a different like class 1 and 10 100,000 10,000 and 100,000, like that. And for performing a photolithography, the clean room also has a UV free lights. So this in the diagram you can say in IIT Mandi, they have the clean room facility there. Your body should not be exposed, and it should be completely covered with the PPE kit, all the glove, shield, eye shield, and for the footwear and for the body wear, everything should be there. So in IIT Bombay there is also a clean room facility. So mostly in there are few IITs there you will get a clean room facility. If you want, you can approach and you can work there for your project. So yeah, so this is how the main so if you want a more to learn about the photolithography, I can provide you more slides and some more information regarding this. This is just a basic information that we got that would be useful for solving your assignments in this week assignments, and this will be enough for that. So yeah. Okay, so the what was the question? The question was here, in case of positive, sorry, in case lithography of negative resist involves an additional post-exposure baking steps, because in the negative, why it is required for cross-linking the resist. Okay, so in negative, we want to be cross-link the resist. Okay, so this would be your right answer. Then next question is here. In case of positive photoresist, pattern on the mask is opposite side of the desirable. Pattern on the mask is the same size as desirable. Pattern in the mask prepare a certain offset and accommodate shrinkage. So it is, I mean, the pattern in the positive photoresist is in the same as the desirable pattern. So this will be main right answer, as I have discussed that in the positive resist, it will be same as the desirable pattern. So pattern on the mask will be your same that what we want in our end. So yeah, but in case of negative photoresist, it would be opposite of the desirable pattern. So I hope that this is clear, and this all the questions are clear. So if you will have a more question related to your photolithography and positive and negative photoresist, then it would be easier for you to solve your assignments. So if you have a question, then you can ask. Otherwise, we can yeah, I'll give you a few minutes and think, and then let me know. Then we can go ahead. No question? Okay, if you will have, then you can ask in the next class. So let's move to the X-ray lithography. So yeah, so in the photolithography, the next is our X-ray lithography. Okay, so here in X-ray lithography, one uses your X-rays to pattern structure into a polymer. Okay, there we are exposing to the UV light, but here we will be using the X-rays to pattern structure into a polymer. The aspect ratio, which you know that it is nothing but the height to footprint ratio and is several orders of magnitude higher due to very short wavelength. Okay, X-rays penetrate deep without diffraction. Okay, so here if since we are using X-ray, so it has a very short wavelength, so it can be short wavelength means the high energy, and it will penetrate your film very deeply without any diffraction. Okay, so X-rays degrade the polymer due to their very high energy. Since it has a high energy short wavelength, so when it strikes to your samples, what it does, it starts degrading your polymer due to its high energy, very high energy. And there are specialized X-ray resist. Okay, most commonly we can use, you can use it's your PMMA. I forgot the full form of this PMMA. I think some polymethyl methacrylate kind of a this. So yeah, you can, if you will be using that, it is a X-ray resist. So it will penetrate. It will X-ray. It will degrade your polymer. Now the X-ray masks are made of X-ray absorbing metal, right? So there will be some X-ray absorbing metal where you will make a mask. So what we will do, we will put a mask on top of our pattern. Okay, now the place mask, the other part, sorry, the main the which we want to expose to our X-ray, that will get degrade when we will hit through our X-rays, and the other portion of the mask that will absorb our X-rays. Got it? So this metal could be your gold as well as lead. So this structure of X-ray transparent substrate. Okay, example graphite you can use. So process is used for making one master mold, resist structure. It will be there. Then electroplating, then resist strip, then metal mold. The combination of this lithography, electroplating, and molding is known as X-ray LICA. Okay, so there is a three process: the lithography, then electroplating, then molding. So this combines will X-ray LIGA. Okay, so LIGA is a German term which is acronym for lithography. Okay. And what is the other form? Li is lithography and galvanoforming is for G and F forming is for A. The technology, it was developed at the Institute of Microstructure IMT and Karlsruhe Institute of Technology in Germany. So this has developed in 1980s. Okay, so yeah, this is very good techniques. In some cases, you can use this for masking your pattern. And X-ray lithography is performed at synchrotron radiation sources which are large. Okay, so this is very high. I mean, what to say? High maintained equipment synchrotron. So there it is very it it is very it is not available everywhere in India. I think there is one or two, so which is in Indore at Raja Raman Center for Advanced Technology. But yeah, there you can do. And electron beam is accelerated in a magnetic dipole which causes energy loss in the form of X-rays. Okay, so here in how X-ray produced, so there will be the electron beam, and this electron beam will accelerate in such a manner in a magnetic dipole will be there, and which will lose the energy in the form of your. So here you can see a synchrotron radiation source will be there, and here your X-ray beam line. This will be, and here electron move is accelerated in magnetic dipole, and this is a few meters to 1 kilometer, and this will lose the energy and the X-ray will come out in the as a product of your loss in energy, and this will hit. So this will be like that, and the wavelength filtering will be there for the various application. And apart from the X-ray lithography, you can have a yeah, as I have explained, UV lithography was developed as an inexpensive version of X-ray lithography. Since synchrotrons are very expensive, it is high maintained and very expensive. It is not always uh, it is not always possible to maintain such kind of instrument. So here you can see in this diagram. So here you will have your silicon wafer, and then on top of this, this is pattern. This is your silicon, and this is for your positive resist. This is your negative resist. Okay. So X-ray lithography. This is your conductive substrate and electroplated mod, and here you will grow your film like this. Okay. So I hope it is clear. So here the main difference is here. In the earlier photolithography, we are exposing our film to the UV such that it in the case of positive, where we wanted our pattern so that polymer will start degrading and we will easily get remaining part as our pattern. But here we are using a very high energy X-ray such that our polymer starts degrading. So this is very expensive method of doing this, but in some cases we need to do this. Okay, so I hope it is clear. Now the next one is our nano imprint lithography and hot embossing. So lithographic techniques can be batch or serial. In photo or extro lithography, the properties of the resist are chemically modified. Okay, here we are using some chemical and developing and making our pattern. In nanoimprint lithography, the short form is NIL. A pattern surface is used as a stamp. Okay, whatever we want the pattern, that will be used as a stamp. Here earlier we were using as a chemically modified register, and this stamps and it will be pressed inside the resist which is hardened afterwards. Okay, so here we will have one stamp of some certain specific design that what we want, and that we will press inside our resist and we'll get it hardened afterwards. Any doubt? If you have, then you can ask. Yeah. So here what we will do is hardening could be due to temperature reduction. Okay. Mold inserted above the glass transition. So what we will do, the mold which will be above the glass transition temperature, and then it will be cooled via thermal cross linking or via thermal cross linking. Large area pattern can be used, but not very high aspect ratio structures would not be used. Mold material should be inert and it should be smooth, like especially the side walls, which needs to be make a contact, and high temperature resistance. Sometimes tapered for easy mold removal. Okay, so it should be tapered so that your mold can be easily removable. And this methods are fabricated by electron beam lithography and X-ray lithography, etc. After mold or stamp removal, leftover resist will be there, and that will be removed by using etching. Okay, typically we can use a plasma etching, and then the commonly and hot embossing are very similar techniques which nowadays use the same machine. Hot embossing is basically stamping a hot material and cooling it to solidify. Hot embossing was reported before, but are now before this technique, but it is now merged. Now UV anneal is another variation where your resist is cross-linked by exposing to the UV light and after the mold insertion. Okay, so when you will insert your mold, then you will expose to it to UV light. So this is usually what we do in the UV anneal. And substrates in UV transparent. Types based on fabrication, plate to plate, roll to roll, roll to plate, and there are some variation. You can apply heat simultaneously while exposing it to UV. You can expose it to the laser also. You can make some pattern by using your laser light, and electric field assisted and reverse nil would be there. Optimization, thermal expansion will be there, release of solvent gases, and the resist viscosity, mold removal damage. So it all this all will be there. So here you can see in this plate to plate nano imprint lithography 1 to 4. And so what would be there, this will be your substrate and this is your resist. So here what you will do, as I have discussed in there will be the your mold and a stamp will be there, and this will be pressed inside your resist. Okay, so this will be like mechanically forced inside your, so yeah, this will go like this, and so this will make pattern here. So as you can see the place which are empty, so this will make a pattern like this. Okay, after that it will remove, then the leftover part will now become like this. Now this resist removal by we can use okay, this place there will be resist and this can be removed by your plasma. Okay, so this is your plate to plate. In roll to roll, here it will be in a rolling format. Okay, so here what we will be doing, here your resist will be there and it will be like rolling and rolling, and it will make a this kind of a pattern. Okay, by rolling, because it has this kind of a structure. Got it? In roll to roll, here it will be like this. It will be rolling, and here because of this, this will be your resist will be coming, and here it will get impact on your this. So yeah, there are different technologies like roll to roll, roll to plate, plate to plate, where you can give your pattern and expose to the UV and etch out the remaining part. So this is how you will be doing your nano imprint lithography. So here basically it is very easy and very doable. The only thing which you required is the mold of your pattern, that what you want, and you have to give some pressure and just press inside your resist in order to get the stamp, the pattern of your stamp. So yeah, this is a nano imprint lithography. Hope it is clear. If any doubt, let me know. So yeah, now we will see the activated carbon after this lithography. So in the introduction, the active surface with physical or chemical ability to absorb molecule, that is called the active surface, where you can easily absorb the molecules and the ability to absorb the molecule. Okay, whether it could be physical or chemical. Now the molecules commonly absorbed on activated carbon are heavy metal ions, could be microbes, etc. Non-graphitizing carbon, as I have discussed in the previous lectures, in I think third or fourth, what is non-graphitizing carbon that cannot be converted into your graphite even at a higher temperature. Even when you be exposed to the higher temperature, it can't be converted. So that is called the non-graphitizing carbon. Material formed by carrying mechanism are mostly porous, so which I also explained this mechanism, this and the coking. And their pores have fractal geometry, and they are micro, meso, macro porous. Micro, okay, so this is in the range of micro, and meso it's not like randomly distributed. Macro pores, due to pores this carbon already have the ability to absorb gases and the liquid molecules because it has a porosity. Okay, so that this feature or this property will leads this material to absorb the gas and the liquid molecules. Now this further enhanced by the physical or chemical activation. Activation typically generates a larger number of micropores and increase the active surface area. Area available for adsorption is called active surface area, where your mainly the adsorption will happen. The volume, total open pore volume. Okay, so here generally the char type carbons are activated, but it is also possible to activate carbons formed by the coking. So here you can see what is macropores is greater than the 50 nanometer. Mesopores, which is in the range of 2 to 50 nanometer. And micropores is what? 2 nanometer range. Okay, less than 2 nanometer. So this is something which is available here. So this mainly feature will give you the property of your absorption, where you can absorb the liquid molecules and the gases. So the activated carbon is term used for the carbons with activate surface greater than 98% element purity, and other material forms by carrying at lower temperature may also have an active surface but lower purity. So this is something where your activated carbon can be used. Now this process here, activation method, how it will get activation. So it has a induced porosity. Okay, it will have some because it's made by the carrying, so it has some porosity. Okay, so that will increase the net surface area. Surface area will increase. Okay, so second is your add active functional group on the surface. So here what we will do, you will add some functional groups. Now, first one is your physical activation. So in this, we will do the heat treatment of your of the porous carbons and prepared at low temperature removal of tar. Okay, so here we will apply some temperature so that the tar can be removed. Now heating it 800 to 1000 degree under an oxidizing agent. Oxidizing such as we can use the oxygen, we can also use the air or the steam. So in this condition, we have to heat it, and this leads to gasification or the oxidation of some carbon on the surface. Okay, so there will be carbon that will get oxidized. Now the water molecules diffuse inside the pores because it has some porosity. So water molecules will come and it will diffuse and block the further gasification. In any case, some carbon is lost during the activation. In the case of chemical activation, what will happen? Performed for natural materials such as wood, usually dehydrating chemical is added to the wood before pyrolysis. Okay, so here we will add the this dehydration chemical and pyrolysis to degrade the cellulose. So in the wood you will have the cellulose. Okay, so that will get degraded. Some common dehydrating agents are phosphoric and the sulfuric acid that we can add. Now, the zinc chloride and the metal hydroxides, carbonates of some metals. Porosity measurement techniques is there that you can use, that how much the porosity or the surface area of your porosity. First one is your gas adsorption isotherms, mercury porosity, X-ray tomography. Yeah, here this I have known, I have used. So here by using this X-ray tomography, you can use the surface area of your porosity, magnetic resonance imaging. So these are some characterization techniques that where this can be used to see your porosity. Now the glass like and other carbon materials are activated and relatively harsh condition chemicals, but they have closed pores, hence the adsorption does not increase much. Okay, so here you can see the surface area is increasing. Okay, so here you will get the porosity. So yeah, this is like this. So what is the absorption mechanism and what are its applications? So anybody knows that what is the adsorption mechanism? What is this? Anybody know? Now, the adsorption mechanism and applications. So, in case of porous carbons, the heat treatment may sometimes be performed at lower temperature, okay, at around 800 to 900 degrees centigrade, because if the graphitic crystallites are increased, the porosity might decrease, okay, because when you will go to the very, high temperature, then sorry, it perform a low temperature because the graphitic crystallites are increased, okay, when you will expose to the low temperature, and the porosity will be increased, sorry, might decrease, okay, because the crystals are increasing, so more porosity will be there, because electrical properties and purities are less important. Basic pore networks is generally this pore networks at what temperature it is formed. This question can be asked, and at around 500 to 600 degrees centigrade. Some pores are blocked by tar, which needs to be removed. So, okay. So, in order to get more porosity, you have to remove this tar, which block the pores. Depending upon the desired purity, heat treatment temperature can be determined. So what purity you want, and what is this adsorption mechanism. So, single layer or multi-layer deposition of the molecule of adsorbate. It could be liquid or gas. So here what we will do, it could be a single layer or the multiple layer deposition of any molecules that needs to be adsorbate. So the hydrophilic functional groups that attract water molecules. Okay, hydrophilic means it will attract the water. Hydrophobic means it will repel the water molecules. So the porous carbons are generally hydrophilic, so it will attract the water molecules. Now the application of these carbons could we can use in the water filtration columns, okay, and as a air purifiers, in the exhaust purifiers, colors. Why? Because it has a porosity, okay, so these properties can be used. Odor removal, especially those caused by the organic impurities. In pharmaceutical industries, we can use this in energy storage device. So these are the application areas where you can use our adsorption mechanism. And this activated carbons, and which are also used as a catalytic beds, they absorb the reactants with an increased residence time, with not participating in the reaction, and product can be dissolved. So what are the available types of activated carbons? Powder activated carbon, granulated activated carbon, spherical activated carbon, impregnated carbon, polymers coated carbon, activated fiber. So yeah, these are the things. And absorption on activated carbon surface, it is how. So here you can see the firstly this has absorbed, and here after this layer the multiple molecules are coming and absorbing. So it is like a single layer or the multiple layer by layer absorption will happen. So this is how you have to expose at certain temperature in order to get some porosity, and there could be some tar which you need to remove. So basically there is a temperature where your pore network forms, so that you have to maintain. Now, the activated carbon industrial production, how you will do in an industrial level. Up to the research, it is fine, but if you want to do in an industrial level, then how you will do, how we can do. So the porous carbon are prepared by low temperature, generally up to 1000 degrees centigrade. Okay, so this is the temperature where you can prepare your porous carbon. Now, the heat treatment of natural polymers are followed by the activation. Common precursors we can use is your cellulosic material, which is wood. Some bituminous and brown coals, peat. Also, these are the types of your coals. Cokes that undergo softening can be pre-oxidized prior to the carbonization, so that there won't be any impurities on all. Just you have to be pre-oxidized at this temperature. So here what you will see, here you will have the your precursor. Okay, so you firstly you will be crushing to get a smaller particle, and you will do the sieving so that you can filter this. You can get a desired size. Now the pre-treatment you have to do, and the crushing and milling. After crushing, you can directly go for the carbonization, and here also. But if you will go for the milling, so you can add some binder. Okay. Now you have to do the extrusion or drying, and then you will go for the carbonization. Then use activation as we have discussed in our previous slide. Now after that, again you will do the sizing or the sieving, grinding, and then screening. After this parts, we will go for your conditioning. Now what we will have: granulated activated carbon. We can have in a powder form, very small like this, or we can have a pellet of this activated carbon. So three forms we can get, like a granule, or like a powder, and like a pellet. So two main strategies that we need to apply here is the shaping the precursor. Okay, we have to give some shape before carbonization. So here is your carbonization. So we have to give some shape by using these techniques. Okay, and after also carbonization, you will get also we have to do the shape like grinding, screening, and sieving. So before carbonization and after carbonization, we have to give some shape. Okay, so this is required for your industrial grade production of your activated carbon. Okay, now rotary kiln. So if you have been through any extractive subject where you have seen this, or the subject where you have seen this, how this rotary kiln works. So basically, this is the types of furnace, or you can say the reactors you can see in any plant. So a rotary kiln is one type, multiple hearth furnace, and fluidized bed reactor. So if you are from a metallurgical background, you must be very well known to this furnaces. So rotary kiln is how it works. It will be a large tube. So here you can see a very large, okay, tube. So it will be a very large tube like setup with char inlet. So here it is your inlet. Okay, so char will inlet from here. Okay, and what you will get as a product: activated carbon as a in the outlet. This is your outlet. So the tube rotates during the operation. So this will be your tube will in a rotation. Temperature increase towards the opposite side. Okay, so here you will have a lower temperature, and when you will go to this side, you will get a higher temperature. They are generally heated using the hydrocarbon fuels. Okay, so you will there is some portion here where from where you can give the hydrocarbon that can be served as a fuel gas. Okay, so here you will put your char, and slowly it will come and it will start, and the temperature will be there, steam and hot gases will be there, and these are your tire one, and this two. This is your gas outlet from where the gas can come out, and when you will expose to the high temperature, here you will get a activated carbon. Okay, so this is a distribution of your temperature here. So this is how rotary kiln look like. This is a pictorial image. So what are the advantages of using this rotary kiln is that the rotation of particles enables large surface area that comes in contact with the heat and steam. So because it is continuously rotating, then I mean the large surface area will come in contact. Okay. Particles move towards other side due to inclined shape. So as you can see, it is not a flat. It has, this kind of a inclination. It's not like a, sorry, it's not like a very straight. So due to large temperature gradient, so here the temperature is low, here the temperature is very high, then it can be controlled in precise manner. Okay, rate of production depends on the rotation speed that you can maintain, and what are the angle of your kiln inclination, and what are the feed rate. Feed rate, it means how much char you are putting, and what is the steam injection. So here also steam will be there, that will create that will contribute for the increment of your temperature. Rotary kiln can always, can have a capacity up to several tons. Okay, so here you can give a production. You can have production in a, tons of tons, because it is mostly used in your industries, and the temperatures can reach up to 2000 Kelvin. Okay, so operating conditions can be determined simulating the mass balance, energy balance, and the heat transfer. So these are the three parameters that you need to optimize. What are your mass balance, what are your input and output, energy balance, what are the temperature you are applying, that means, and the heat transfer. It means that what are the temperature distribution throughout your this rotary. Okay, how you are distributing your temperature, that will determine your, that is the operating condition that determines the process. I hope it is clear. If not, then let me know. We can discuss in our next class. Now, the multiple hearth furnace. So, so as from the name itself, it is clear you will have a multiple this furnaces. So here you can see, yeah. So this is a kind of a image schematic. So here you can see the char inlet is will be there, and it will come, and this is what your it is a rebel arm. Okay, and this is what in hearth, and here will be your burner, so it will give you the temperature. So there will be a lot of burner, and it's like this, and here your this will come, and it will come like this. From here it will come here, and then here to here. So yeah, there are multiple steps, there are multiple hertz, so through which your char will come, and it will expose to the different temperature across the temperature gradient will be also there. And then your activation carbon at last you will get as end product, and this will also keep on rotation. So this is also one outlet, and from this side you will have your gas exhaust. So multiple hearth furnace contains various heating and cooling zones where different process takes place. The first one is your drying, pyrolysis and combustion, fixed carbon burning and ash cooling, and hot gas flow upwards. Okay, so here your char will come downwards, and your hot gas, you know hot gas will flow upwards, and your steam carbon dioxide can be injected, and multiple stages and lower residence time, hence slightly inferior carbon quality, because it has a lower residence time. So the quality is not that very good, but yeah, there are some optimization parameters that needs to be optimized in order to get a good quality. The number of hertz, so here you can see we have like a one, two, three, and there are like eight. So, and the rotation here, it will be on a keep on rotation. And speed, what are the rotation speed, and what are the temperature you are giving, what are the feed rate, and yeah, there are a lot of parameters that you need to optimize. So this is also the same, but in rotary gun you will have some inclination kind of a tube. But here it is like a multiple hertz. You will expose to the different temperature, and it is like a layer by layer. It is in a rotation period, so it will come like this. In fluidized bed furnace, you will mixture of solid particle including fluid which has a net fluid like behavior. Even though this is a heterogeneous fluid, single bulk density is assumed. Fluidization enables extended residence time for any chemical reaction or gasification. Solid particles have a free flow. They experience steam, hot gases, all surface. Better heat transfer due to high velocity of the fluid. So here you will inlet will be your charge, and this is how fuel will come from this side, and fluidized bed with char particles will be there. This will be like a bed. So for the better image, you can search in your Google, you can have some better images, and the steam and the gas will be there. So the fluidized bed requires very short residence time. Often reaction is too harsh, and mechanical damage to the particles can take place, and here there would be a loss of your carbons, and also not possible to control here properly. And it also uses powdered activated carbon. Most commonly it is used, and used activated carbons of all types is reused after reheating desorption of the adsorbed impurities. So yeah, these are the three steps: the fluidized plate furnace, multiple hearth furnace, and the rotary kiln, where you can produce your activated carbon in an industrial manner. So if you have any doubt, I can explain in a more detail in further class, and let me know. So there was some few questions which I want you guys to be solved. I will give as a homework. If not, then it is okay. I will give you some hints. So these questions on the basis of what we have covered in our this concepts. So the question is, negative resist are used for making MEMS device. Why? Because they have relatively higher viscosity and structure with high heights can be obtained. They yield low quality carbon and heat treatment to be used MEMS device. They are inexpensive compared to positive photoresist, and they have a high availability of developers on obtain. So here, if you have seen in the concepts or the topic where I was discussing, it has somewhere related to your heights, why we are using. And in the positive resist, you have to, you can make some very thinner kind of a film, but here you can make some heights, and that's why it is mostly used for the MEMS device, and also because of the high viscosities. So somewhere I think it is related to the viscosities and the height of the structure you want. So this is probably the reason. But anyways, if you have something more to say, then you can put in the comment box. The UV dose of for a resist is determined according to the film thickness. Okay, so smallest feature size on the pattern, presence of solvent in the resist, viscosity of it. So I think in our this slide we have seen that whatever we want the film thickness. So I think it is somewhere related to the film thickness. So if you want to expose your film to the UV, then you require for the UV dose, and that is I think depend on the film thickness probably. And let me know if you have any other comment, or if any other factor which affects this, then okay. So yeah, this is all for today, and let me know if you have any questions, you want some more numericals, or if you want any more concepts to be discussed. Feel free to mail me or contact me. So yeah, this is all for today. Thank you so much for attention. Yeah.